Hello, Sauce here. This is a lesson on solving a system by graphing. And let's remind ourselves, a system is a problem that has more than one equation. So a solution to that system is finding values for the variables that make all of the equations in the system true. And this time, when we solve a system, we're going to do it by graphing rather than algebra. So here's an example of a system. I have one equation, y equals 4x minus 5, and a second equation, y minus 9 is equal to 3 times x. And if I put a bracket that groups these equations together, I can be clear that I'm thinking of these equations at the same time, and the solution then would be finding values for the variables x and y that makes both equations true at the same time. So the direction for our example would be to solve by graphing. We can solve this with algebra techniques, but this time we're going to show it by graphing both equations on the same axis. So I'm going to draw axes. An x and a y axis. And I'm going to graph these lines one at a time. The first equation, y equals 4x minus 5. Of all the graphing techniques I'm going to use, I'm going to think of this as an equation in slope-intercept form from a previous lesson, where the y-intercept is negative 5, and the slope of this line is the 4 that multiplies the x. How can I graph an equation in slope-intercept form quickly? Well, I put my first point at the y-intercept, so I'm going to find where negative 5 is on the y-axis, and put a point there. The y-intercept crosses the y-axis. This line will cross at negative 5. And then I'm going to use the concept of the slope. The slope of the line that I'm graphing is 4. And use that concept, that means that for every 1 I go over, or for every 1 I increase x, then I'm going to go up or down the amount of the slope. In this case, it's a positive 4, so I'm going to go up by 4 to find another point. I'm going to find a third point by using the slope concept again. For every 1 I go over, I change the amount of the slope. In this case, it's a positive 4 to find another point. I've got a few points here. If I connect them together, this line represents all of the solutions to the equation that I just graphed. That means that every point that is on this line is an x and a y value that makes that first equation true. I'm going to graph the second line, but I'm going to use a different technique. It's not obvious to me that this is in slope-intercept form, so I'm going to go to my most reliable method of graphing, which is to organize a t-table of points. The t-table method works for graphing anything, but it's a little slower. In the t-table method, I have a column for x and y. I'm going to make some choices for x, in this case 1, 2, and 3, and then I'm going to use the equation to calculate the y value for my choices. If I choose x is equal to 1, I'm going to do a side problem, rewrite this equation, but substitute 1 in for x. Here's my side work. Rewriting the equation, y minus 9 is equal to negative 3 times my choice for x right now is 1. I'm going to solve for y by simplifying this. Negative 3 times 1 is negative 3. Now to get y by itself, if I add 9 to both sides, Negative 3 plus 9 is 6. So when x equals 1, y is equal to 6. This is an ordered pair that I can graph and plot a point immediately. This is the point x equals 1 and y equals 6. That point right there. But I need more points. I'm going to do side work when x is equal to 2, rewriting the equation, choosing x to be 2. Quick calculation. Now I have to add 9 to both sides. Negative 6 plus 9 is 3. So when x is equal to 2, y is equal to 3. One more side work problem. I'm going to choose x to be 3. Adding 9 to both sides gets y by itself, and negative 9 plus 9 is 0. So when x equals 3, y is equal to 0. I've got 2 more points to plot. The point 2, 3 is that point right there, which I've already graphed on the other line, and the point 3, 0. 3, and then 0 means that I stay on the x-axis. I used the second equation. I made a t-table. I plotted some points. If I connect them together, then this line that I just graphed represents all of the possible x and y values that make the second equation true. That's what a graph is. A graph is a representation, a visual representation of all of the possible solutions. But I've got 2 lines graphed here, and there is one point that is on both lines. This point of intersection is a point that is on the first line that I graphed, so it's a solution to the first equation. And this same coordinate, 2, 3, is also on the second line that I graphed, making it a solution of the second line as well. So if this coordinate right here, where x is equal to 2 and y is equal to 3, is on both graphs, then it makes both equations true, then its values are a solution to the system. In general, then, we can find a solution to a graph at the points of intersection. So let me update my definition. The points of intersection on the graph of all equations. I've updated my definition of a solution to the system. It is now values for the variables that make all equations in the system true. In this case, the values were found to be x is equal to 2 and y is equal to 3. And a solution to a system is the points. There might be more than one. In this case, there is only one. The point or points of intersection on the graph of all equations. So I found that point of intersection by graphing first and observing where they crossed.